Okay. All right. Good morning. Thank you, Jacqueline, for the introduction. Good morning, ladies and gentlemen. My name is Roland Nuits. I'm from SurfNet in the Netherlands, and the title of my presentation is Optical Networking for Mainstream Research and Education Networks. Let me give you a brief outline of my talk. First, I'll introduce SurfNet a little bit. Then I'll give you an overview of the status of the SurfNet 6 network. I'll discuss user-controlled light path, also DRAC after that. Then I'll elaborate a little bit on the enabling technologies for dynamic wavelengths switching. I'll discuss the dynamic wavelength grid, the supercomputing grid project that we are running in the Netherlands. And finally, I'll discuss the future plans of SurfNet. Now, what is SurfNet? SurfNet is the Dutch NREN. Most of you probably know this already. It's a not-for-profit organization. We have 60 employees. It's 100% owned by the connected institutions via the foundation SURF. Right now, there's about 180 connected institutions and about 750,000 end users. Those are mainly students. We get part of our funding from subsidies for innovative projects. It's about 14 million euro per year. And another big part comes by the tariffs that the connected institutions pay. That's about 18 million euro per year. Now, how did we get to the SurfNet 6 network, which we are using now? This slide shows the SurfNet network capacity evolution. And it shows that for the past 20 years, the required capacity has doubled roughly every 40 weeks. So now when we are operating SurfNet 5, which was roughly from about 2000 to the end of 2005, it dawned on us that you can't just increase your IP routed capacity at this rate because it comes way too expensive. So what should we do then? So we looked at, first this is actually a slide courtesy of Kees de Laat of the University of Amsterdam. We categorized our users to see what would be the good thing to do. So basically, or roughly, there's three categories of users. There's the group A, which is the end users. They mainly use the network for connecting to internet or for email. So all routed traffic, and these are mainly, well, the students. Then you have category B, which is the institutions. They mainly use the network for applications and for setting up VPNs and shared service centers. And then category C is the researchers. They use the big fat data pipes. So they use the connections to the telescopes, for example, to download data, or connections such as the connections to the LHC, the Large Hadron Collider. And we decided in SurfNet 6, the good idea was to have these latter category use their own light path, point-to-point connections that are not going through the routed core. And by doing that, you create a hybrid network, where one part of the traffic is going through the routed core and the data-hungry applications are detoured around the IP core. So this slide illustrates the network that we built then. As you may know, we decided to use, or the result of the tendering process was to use Nortel equipment. We used the Nortel OME 6500 for the light path connections, and then the 8600 and the 5000 to transport the IP traffic to the routed core. All the parts in orange at the bottom. So these locations are the customer equipment. So they connect to the demarcation point on the 6500s. This slide then shows the services that we support on the SurfNet 6 hybrid network. So they're divided into IP routed services and light path services. And then IP routed services, again, is subdivided into IPv4, IPv6, and each of them in unicast and multicast. In terms of light path services, we offer static light path services, single light paths, and OPNs, optical private networks. That's nothing more than a set of light paths that connected institutions use to set up their own private network. Those are actually quite successful. We have about 25 of them now. And the total number of, well, point-to-point circuits that's used for all the light path and OPN connections is now about 220 in the SurfNet 6 network. We also offer the dynamic light path, and, well, that's supported by DRAC, and I'll get back to that later in the presentation. Now this slide shows on the left, well, the geographic locations of the POPs, the points of presence in the Netherlands, and on the right-hand side is the system configuration of the network. Basically, on the right-hand side, in the colors, those rings, those are the WDM systems. So we have 5 of them. 4 of them all terminate in Amsterdam, and there's one here in the southern part of the country from Eindhoven to Nijmegen that connects to the other rings. We also have 3 cross-border fiber connections now, 1 to Hamburg, 1 to Münster in Germany, and 1 to Aachen in Germany. The top one to Hamburg connects to Nordinet, our friends in Scandinavia. So those are, well, right now that transports their IP connectivity or a backup for their IP connectivity, and, for example, a connection to Ripon in Russia. The connection via Münster supports the GridK project, and the link to Aachen is for Philips Research. Philips Research is located in Eindhoven and is a customer of SurfNet, and in Aachen they also have a site, so they were one of the main drivers for installing that cross-border fiber. And as it shows here in the bottom, right now we have almost 9,000 kilometers of dark fiber pairs in use. Those are all leased for about 15 years. Recently, the power consumption is becoming a hot topic. So when we were here, we did a quick back-of-the-envelope calculation of the power consumption in the SurfNet 6 network. So on the left, it shows what that constitutes, about 14 head-end WDM sites, 21 OADM sites, about 166 optical amplifiers, if you count them unidirectionally. Right now we have 115 WDM, 10 gig links. Of course, the 2 core IP routers in the 2 sites in Amsterdam, and well, several TDM rings that come off the DWDM rings. And the total power consumption of all that equipment is less than 100,000 watts, so that's really equivalent to like a medium-sized car. So it seems that for the backbone transmission, that power consumption is not really such a big issue. In data centers and for storing servers, it is, because there the power consumption per rack has gone up tremendously in the past years. But in the backbone transmission, it doesn't seem to be such a big issue. This slide shows an overview of the dark fibers we use for the WDM systems. As you can see, a bit more than half of that is still standard fiber, and actually a lot of the dark fiber suppliers continue to install standard fiber when they install new fiber. About 43% is true wave RS, and about 5% is large effective area fiber. So a total of 2,955 kilometers, and well, the measured absorption coefficient is about 0.25 dB per kilometer. You still see that in a lot of them they have some connections on the way, and that increases the total loss and also the average absorption coefficient for that reason. The graph in the bottom left shows the distribution of the fiber span length. It shows that, well, most of the spans have a length of about 80 kilometers. That was also the maximum length in our CFP for fibers. The reason is probably that most of the equipment is targeted for the North American market, and a long time ago they used 1310 nanometer transmission, and 40 kilometer spans was the maximum distance. So for their long distance routes, everything is almost 40 kilometers, and well, since the arrival of 1550 nanometer transmission, they connected those 2 spans to make one spans of 80. So the majority of the spans there is 80, and that's why system designs are targeted pretty much for 80 kilometer span lengths. So that's also the case in our case. And then, of course, in some cities you get shorter spans, and in some cases you have no choice. You have to go further than 80 kilometers. So this is actually one span of 110 kilometers, which is the CBF to Germany, to Münster. This slide shows well, the market share of the different dark fiber suppliers. We have now 10 suppliers. 3 of them will provide about 75% of all the fiber, and there's a consolidation going on in that business. Actually, about a year ago there were 4 more, but by now they have been absorbed by some other of them. So, and that trend goes on. We expect that this year about 2 or 3 will disappear, so reducing the number of suppliers to 7. One thing that you have to be careful when you acquire or lease dark fibers from so many different parties, you have to make sure that you know where those fibers are. And for that reason, we entered into agreements with all of the dark fiber suppliers to provide us the detailed geographic route information. And they do that now. We entered into a graphical database, and then we can actually have the database spit out the places where there's a possible single point of failure, so that we can use that information when we build new circuits. Where should the working go? Where should the protection go to avoid single points of failure? The NREN National Research Education Network does not stop at the border. We have several international connections. And this slide shows an overview of all the Netherlands connections that we have. Top right is the link to Hamburg that I just mentioned. Actually, the ribbon link to Moscow is actually now also carried by this system. And obviously, these are all multi-domain light path, and the monitoring of those has a couple of challenging issues. And actually, Ronald van der Pol, who's the next speaker, will elaborate more on the monitoring of these links. As I mentioned in the introduction, we're also working on DRAC, the Dynamic Resource Allocation Controller. This is DRAC is developed in a close collaboration with Nortel, and it allows the user to set up a temporary light path, so you can enter the 2 ports between which you want to set up a connection. You can enter the desired speed. This can go actually between 0 and 1 gig, but since recently, DRAC can also control 10 gig connections in the WDM systems. And then here you can enter start time, begin time, end time. So the user is in control and can set up his own schedule. This year we are planning to do some pilot tests with a small group of customers, and then the idea is that by the end of November this year, DRAC will be widely available as a service for all the users in SurfNet 6. Now, network agility. When we built SurfNet 6, the WSS functionality, ROADMs, were not available yet, so everything was fixed, and right now we're in the process of changing that. There's basically 2 technologies that you need. First of all, in your connections, in your cross points in the network, you need to be able to dynamically route the optical wavelengths. And then also, of course, since your path changes, for example, first you go from this side to here, and then you go to here, your path length changes, and your dispersion compensation has to be changed. So you have to be able to dynamically adjust your dispersion compensation. Now, there's 2 advantages if you can do all that. First of all, in the nodes in the network, you can do all optical wavelength routing, so you don't have to do regeneration, which saves you a lot of money in terms of equipment. And second is, once a WSS is installed, you don't need to visit that site again in principle. So when you set up a new wavelength, you can just remotely configure those nodes where the wavelength should go. So that's 2 advantages: reduced capital expense and reduced operational expense. So I'll talk a little bit about the technologies that make network agility possible. Well, first of all, back to dispersion. So as you probably know, each modulated signal, so for example, a 10 gig signal, as is shown here in the time domain, has a spectrum associated with it in the frequency domain with a certain width. So for example, for a 10 gig signal, it's about 20 gigahertz, which is this main lobe. The information outside that bandwidth, these lobes you can throw away. That won't change the signal much. Now, what is dispersion? Dispersion means that light, the propagation delay of light changes with wavelength. So that basically means that these spectral components travel through the fiber at different speeds and arrive at the other end with a delay. Now, in 10 gig, this 1 bit is about 100 picoseconds wide. And you can imagine that if this frequency component here and here at the extremes of the spectrum, if they have a delay of about 100 picoseconds, that, well, the signal gets quite distorted. So you can calculate at what distance that happens in case of standard fiber. So that's about 50 kilometers for, in the case of 10 gig transmission. So if you want to transmit further than that, you need to do some kind of dispersion compensation. So when we rolled out our network, we put in bulk compensation everywhere, so dispersion compensating fibers, which is fixed. And also, it is not optimum to do 100% compensation of the dispersion, but a bit less. So in each ring we built, you will see that there's a little bit of undercompensation. That's fine until you want to concatenate a couple of rings. So for example, if you go to 3 rings, you have 3 times the undercompensation, and then either you lose some of your margin, or in the worst case, your connection just won't work. So that's why you need to do some dynamic dispersion compensation. Now, in the equipment that we use, that's implemented by doing pre-compensation at the transmitter end. So basically, in a transmitter, you have 2 Mach-Zehnder modulators. One is used to pre-compensate the intensity, and the other one to pre-compensate or pre-distort the phase. And what happens then is that the signal that you send in the fiber is completely distorted, but while it propagates through the fiber, and this is an example after 1600 kilometers of standard fiber, you actually have your eye cleaned up, and error-free detection is possible again. So, and this is dynamically also. When you install these links, transmitter receivers will continuously communicate and adjust the dispersion compensation so it's at the optimal value. Now, that's for the dynamic dispersion compensation. Then to build the ROADMs, you have to be able to somehow select the wavelengths that you send in certain directions in the system. This slide shows the principle of operation of a wavelength selective switch. Basically, the way it works, it's based on a diffraction grading and an array of MEMS mirrors. So what happens is you send in a couple of DWDM input signals. These are collimated by lenses, and then collimated beams are sent to the diffraction grading. Now, what the diffraction grading does, it reflects all the channels in the WDM signal with an angle that depends on the wavelengths. So you'll see that of all these inputs, if they all have a channel 1, let's say that's the red channel, they're all diffracted under the same angle towards this lens, and then the property of this lens is that it will focus all the beams that come in at the same angle, at the same spot, at a distance of the lens that is equal to the focal length. So then if you put your MEMS mirrors in the right spot, in each mirror you will get all of the channels 1, and in the next mirror you will get all of the channels 2, etc. So now by rotating this mirror to the right angle, you can select one of those channels that come in and send it to the output. So that's how, well, the wavelength selection is done in the system. Now, one project where we have used this so far the most is the DAS3 supercomputing grid. That's a joint project between University of Amsterdam, the Vrije Universiteit Amsterdam, Technical University of Delft, and University of Leiden. So we set up basically a optical switch with about 10 point-to-point 10G connections that we can reroute to form different configurations between the supercomputers. Now, the topologies that are used most at the moment is the star network, mesh network, ring network, and those we can change. Basically, now we can do it by DRAC, but DRAC actually talks to the software of the WDM equipment, and for that reason, the changing of the wavelengths takes in the order of minutes. We are also investigating ways to make that faster. So, for example, if you use TL1 commands, we think we can do it a lot faster, but that's under investigation. Future plans. Well, at the moment, we're in the process of further introducing dynamic dispersion compensation, and also we're building more ROADMs in our network. Then that will allow us to do, well, all optical routing of the 10G wavelength, so it saves money in terms of CapEx and OpEx. And it also allows to do 40G more efficiently. We hope to introduce 40G channels this year. One of the possible applications is between LOFAR in Dwingelo and a new antenna field that's being built in Aachen in Germany. Further, we'll also look at multi-domain control plane interworking for DRAC. So if you use DRAC to set up a light path between a point in SurfNet 6 and a point in somebody else's network. We'll test new technology, for example, PBT, provider backbone transport, and we'll further enhance monitoring and reporting. Thank you for your attention. Are there any questions?
Hi, Roland. If you go to 40 gigs, you said that without dispersion compensation, you can go only 3 kilometers. With electronic dispersion compensations, are there any limits how far you can go?
If you look at 10G, the modulation is direct. That means you're turning off your laser on and off at the 10G speed. Our supplier has developed a 40G method where you don't only intensity modulate, but you actually modulate 2 polarizations and you modulate the phase of each polarization. And by doing that, they are able to use to put 40G in a signal that has a bandwidth that is as narrow, maybe a little bit wider than the current 10G signals. So for that reason, you don't really have only the 3 kilometers to go. And then furthermore, they also build in the electronic dispersion compensation. So the 40G transmitters and receivers they built have about the same tolerance as the 10G, so about 2,000 kilometers of standard fiber they can bridge without compensation.
Thank you. Before I introduce the next speaker, I would like to remind you to fill in evaluations. You can either do it on the web, or you can go downstairs and get a paper evaluation, and you will be getting a prize. I don't know what the prize is, but apparently at the registration desk, there's a prize waiting for you if you request an evaluation. And it's, well, probably if you turn it in. I think so anyway. Don't forget tonight's gala reception. It will be at the Belfry in the center of town. And I'm told that the reception itself is outside, so you may need a coat, although it's very lovely and warm right now. So without any further ado, I would like to introduce our next speaker, who is Ronald van der Pol from SARA in the Netherlands.
Okay, thank you for the introduction. My talk will be about the management of dynamic light paths. I will first give a couple of examples, 2 examples of interdomain light paths. Then we'll talk about the monitoring we have currently set up. And then the challenges of dynamic light paths. And I will end with some conclusions. The 2 examples of interdomain light paths are the LHC OPN of CERN and EVLBI. The Large Hadron Collider of CERN, the experiments generate a huge amount of data, and that's not stored locally at CERN, but stored distributed around Europe and a couple of sites outside Europe. All these sites are connected with 10 gig light paths. This is an example of this is how the LHC OPN looks like. In the middle is CERN, the so-called Tier 1 sites that store the data are in France, Spain, Italy, Germany, the Netherlands, UK, Scandinavia. There's one in Taiwan, one in Canada, and there are two in the United States. And they are all connected with mostly 10 gig light path, and some of them are also interconnected. And all these light paths go to several domains. Another example is EVLBI. In this case, many radio telescopes are interconnected with light paths. And the idea is to form one big virtual telescope. The signals of all those telescopes are collected at one correlator. And all these telescopes are basically all around the world and in Europe. And they are all connected through light paths. And these light paths are also going through many domains, administrative domains. The network that's being used for this project is the GLIF network, GLIF facility. All these connections are mainly 10 gig connections, and researchers can use this network for projects like I just described. This is how the European part of the GLIF network looks like, and a big node in the GLIF network is in Amsterdam, that's called Netherlight. This is almost the same picture as Roland already showed. This is slightly newer version, because there's also a link to Mumbai in India at the moment. And there are links to Stockholm, Moscow, Prague, Geneva, Barcelona, couple of sites in the United States, and a 10 gig circuit to Taiwan. And there are connections to the Jan 2 network and the SurfNet 6 network. And Netherlight is basically an optical exchange point. The software we are using to manage both the SurfNet 6 and the Netherlight network is at one side the basic Nortel network management system. That's a traditional system with all the devices, and when there's a problem with the device, it turns red. You can click on it, you get more information, you can look into alarms and get more information about that particular alarm. But that only looks at individual devices, and we also want to monitor the services running over the network, the light paths basically. There was no software at that moment, so we wrote our own software. We started with a Perl version, but it grew that much that we rewrote it in Java. It's now Apache Tomcat based with Java server pages and servlets. And information is stored in a MySQL database, and we also have a topology file. On the bottom are the URLs for this monitoring system for Netherlight and for SurfNet 6. The architecture of this monitoring software is like this. We use the TL1 toolkit to retrieve information from the network, the SurfNet 6 network and the Netherlight network. And this information is, the configuration information is stored in the MySQL database. And we also use the TL1 toolkit to retrieve information about the topology of the network. And we automatically generate a topology file in NDL. And the configuration information and topology information is used by the monitoring software, and that's presented to the client as a web interface. The TL1 toolkit is a Perl module. Most optical equipment uses TL1 as the CLI. And TL1 has quite complex syntax. And the TL1 toolkit hides this syntax from the user, and it presents the user with easy-to-use data structures. It also takes care of connecting, logging in, and logging out of the equipment. And it makes it quite easy to write simple Perl scripts to retrieve all kinds of information from the network. There's an open source Apache 2 license, and this is the URL where you can download it from. The other thing we are using is the network description language framework of the University of Amsterdam. As I said, the SurfNet 6 topology file is automatically generated. We do this by using SDR section trace that sends information over the links, basically telling which device and which interface is connected. And in that way we can build the topology of the SurfNet 6 network. And currently the SurfNet 6 network consists of 12,000 lines, and you can't do that anymore by hand. It's RDF based, and that means that you can use all the RDF tools. For example, Sparkle, that's a SQL-like language, and you can use that to get, for example, a list of all devices, or a list of all interfaces of a device, or all devices in a particular city, and things like that. So in the end, what the network engineer is presented with is an overview. There's a couple of web pages. This is an overview of all the light paths, in this case the netlight, all the light paths through netlight. And in the first column, this shows if there's a problem with the light path. Well, most are green and up, and there's one that is down. In this case, we also distinguish between light paths that have next business day SLA, and then it's turned orange. And when the light path has 24/7 SLA, then we use the red color. You can click on one of those light path names, and then you get more information. The topology of the light path, which devices, which interfaces, information about time slots. Another web page is alarm information. When the alarm occurred, name of the alarm, the devices that is where the alarm is raised, if it's service affecting or non-service affecting. And in this column you see how many services, how many light paths are affected by that alarm. And you can click on this number, and then you get the previous list of light paths again. At the moment this is used for SurfNet 6 and NetLight, so we only see our own domain. But many, especially for NetLight, many light paths are interdomain light paths, and some of the light paths in SurfNet 6 are also interdomain. And we need some kind of end-to-end monitoring. Because when we have a light path that is from the Netherlands to Japan, and there's something wrong in Japan, all the domains in between, and also our own SurfNet 6 domain, sees alarms, and we need to know where the real fiber cut is. And then you have questions about who is informing the end users, who are the end users, what circuit are we talking about. We have our own naming scheme, and other domains have different naming schemes. And when we need to figure out where the problem is, we need to have a global identifier so that every domain can talk about the same light path. For the monitoring part, Persona is being developed. It basically consists of measurement points. Each domain installs one or more measurement points. And these measurement points give information about the links, the topology, and also the status information of those links. And then there's a collector that collects all these information from all the domains and combines it to an end-to-end overview of the light path. Currently, you need to configure the links and the topology manually in configuration files of Persona, and that doesn't scale. For example, Roland already mentioned that the SurfNet 6 network has over 200 light paths, and they are changing, and in NetLight they are changing even more. And when we will get dynamic light paths, then this doesn't work anymore. And then we need to have a way to generate the configuration files for Persona automatically. This is what Persona gives you for an end-to-end view. It's tables like this. You can see which domains. This is for this particular light path. From CERN to SARA for the LHC OPN. At one end it starts at SARA and then goes to NetLight and Geron. All the links are mentioned, and this is the status of the links of that light path. And in this case they are all up. But this gives the information if, for example, if there's a problem in the Geron network, this will say down. And with this overview, the network engineers of NetLight can see that the problem is in the Geron network. So dynamic light paths, they cause new challenges. Last couple of years has been a lot of research going on dynamic light paths. And it's, when you see the architecture pictures of the different systems, it has become quite complex, and especially interdomain, when the different dynamic provisioning systems need to interact with each other and need to cooperate with each other. And of course, this is fine as long as it works, but when there's a problem, then the NOCs get involved. And then the question is, can we expect from every network engineer that he has a good understanding of all these dynamic management, dynamic provisioning systems, control planes, the protocols that are used? Or do we need specialists for that, and how many specialists? So we need to figure out how to do that operationally. For the management systems, there's the question if there's going to be separate management systems for these dynamic provisioning systems, or do we want to try to integrate it in the current monitoring and management systems? And also, when these dynamic light paths are being used, they cause alarms during the provisioning phase. And we need to distinguish between the normal dynamic switching and the real problems, the real fiber cuts. And the problem is that, for example, when you have this light path from NetLight to Japan, and somewhere in Japan the dynamic switching takes place, all the intervening domains and also Netherlands Subnet 6 see alarms, and they don't know, well, they have to figure out if it's because of the switching in Japan or if there's a real fiber cut. The alarms you see during provisioning are basically unequipped alarms. This means when the light path is not provisioned end-to-end anymore, because you are in a state of switching from one path to another path. And also the end ports will give a link down alarm, but that can mean because there's provisioning taking place, but it can also be that there's a real fiber cut. This is an example of that. This is a light path from A to C to D. This is a normal situation, no alarms. And when we are switching this light path dynamically to B, C, D, then there's a moment that alarms are taking place. Because first you have to remove the cross connects on the A node and the C node. That will give unequipped alarms and a link down alarm. Then you build the new cross connects on C and B, and you have an end-to-end light path again, and the alarms clear. And when this is being used frequently, a lot of dynamic light paths are being set up. I heard about Internet 2. They sometimes have days that over 200 light paths are being switched per day. So that will give, in brief times, many alarms, and you have to distinguish between all those alarms and the real fiber cuts. So there are some challenges. We need to figure out how to deal with these alarms, and we have a reasonable understanding now, and it seems like we can sort out a good way how to deal with these alarms. I think we also need to think about the complexity. Now it works, but working is different from operating it. And I think we need to slowly think about making a simplification step and going back to the keep it simple principle. There are some current activities going on in the Glyph community and the research network communities. Persona is an example of that. We need to extend that framework and look at automating the configuration of that. The Glyph community is working on global identifiers so that all the domains can talk about the same light path. And the Glyph community, the network engineers are also discussing all the operational procedures. For example, if there's planned work, how do you tell that to all the other domains? How do you handle real outages? Who is informing end users and operational questions like that? So, thank you for your attention.
Do you have any questions?
Ronald, I have a question about the alarms. Is it possible to overcome the problems of these alarms? Are the alarms caused, or could they be overcome by having a better provisioning system, let's say, of Nortel or something like that? Or are they so basic that they always will happen? And is it possible to have different standardization about it or something like that you don't see alarms when you make a circuit or something like that?
Yeah. Some of them you can't prevent, like the unequipped alarms, but the provisioning system that is being used in, of is going to be used in SurfNet 6, the Durek from Nortel. Nortel spent a lot of time on limiting the alarms that are taking place during provisioning. For example, when there's no circuit present on the port, then there's made a small loop on that port so that it won't give alarms. But the unequipped alarms, you can't get rid of them because that's the way SDH works. And what we are going to do is just say that we are going to ignore unequipped alarms, but have some scripts running, for example, daily, to see if there are leftovers of cross-connects that can cause these alarms also. Well, in the next few months, we'll get operational experience with that, and we can share that with the community and discuss how Direct solves this, and if other provisioning systems can also take a similar approach, and maybe come to some kind of standardization.
I'm always a little bit confused about the meaning of light path. So please, could you explain to us, in few words, what's the major difference between what you call a light path and what I would call a lambda end-to-end connection with some monitoring and maybe management tools?
Yeah, there's been a lot of talk about light paths.
Or is it just, I mean,
yeah.
It would be worse maybe if it's just a good marketing.
Basically, it's an end-to-end circuit. At the moment, it's mostly through the SDH layer, so an SDH circuit. But some are also complete lambdas, and they're also called light paths. But it's basically a circuit that is being used at the end. At the two endpoints, the end users are almost always get Ethernet interface, and so it's Ethernet virtual line.
So it's a generalized channel?
Yes, you can say that, yeah. It can be a LATA channel or a SDH channel, sometimes an Ethernet VLAN.
Ronald, as an operator, I've heard a few talks this week and obviously before as well about circuits on using Ethernet. Roland talked about circuits on the really WDM layer. You talked about circuits on the SONET layer. And they all have problems monitoring. SONET, it seems, has most options for getting information out of the system, for the path, but still you have problems finding it. What as an operator would get you excited? Should the IEEE make new monitoring additions to SONET, or do you see OAM extension to Ethernet as the solution? Something else?
Yeah, if you look at the IEEE and Ethernet, the OEM for Ethernet is being expanded in the carrier Ethernet initiatives. So we are seeing now already that there are more and more facilities for managing, operating Ethernet circuits and Ethernet networks. And basically, for an operator, I don't think it doesn't matter that much if it's a SDH circuit or an Ethernet circuit. It's more a fundamental way of how do you provide these light paths in the future. And many people think that Ethernet will slowly take over the SDH-based circuits. And especially when the Ethernet gets the same management OEM features of SDH, then for the operators I don't think there's that much of a problem or preference.
Any more questions? One last question before our next speaker? No taker? So I will use Chair's prerogative to do some marketing. Our two speakers have mentioned Netherlight, the goal. We have a goal in Seattle too, and we will be hosting the next Glyph meeting the 1st and 2nd of October in Seattle. So I hope to see as many of you as can come. Our final speaker in this session is Aphroditis Sevasti from the Greek Research and Education Network.
So, good afternoon, everyone. I think it's already noon. So, this presentation comes as a nice follow-up of the previous one from Ronald, because it presents some research activity that has been taken within the framework of the GEAN2 project to address exactly the issue of multi-domain circuits or light path provisioning across many different technically and administrative domains. Actually, there are two presentations in this Torino conference for this work. This is the first one. I invite everyone to also attend after lunch in the Strauss Room a presentation of my colleague Radek Rizvania, who will be presenting a more general view of what I will speak about today. He will present the general approach that we took, the system, the experimental system that we designed, and also our efforts to make this GEAN2 result interoperable with similar results in the Internet 2 area. We are also starting now to discuss with Glyph. We are starting to take this effort to other groups around the world. So the presentation of later today gives a wider picture. It is about establishing a global control plane to make these kind of services possible. My presentation is more focused on what needs to be done by national research and education networks to join this experimental, this pilot so far effort. What we're trying to prove is that it is feasible to connect different domains under an interdomain control plane or a business plane protocol to be able to make end-to-end provisioning possible. So I want to make clear that this effort concerns the end-to-end available infrastructure of national research networks, and not dedicated facilities like that of Glyph. So we are trying to address the same problem, but for a different use case, a different set of infrastructures. So, like already mentioned, Autobahn is the research activity within the GEAN2 project, which is trying to devise a framework for automating end-to-end setup of guaranteed capacity paths. GEAN2 is a European Commission-funded project, and the reason why we have tried to address the problem, and we have tried to see the problem from the eyes of the NRNs, is because NRNs are the major stakeholders of this project. So the problem area we're trying to address is taking the existing infrastructures, the available infrastructures to the end users of the research networks. How can somebody coordinate end-to-end provisioning of dedicated circuits when different domains use different technologies, and there is a large amount of information that needs to be negotiated among the NOCs to make this possible. So in this diagram, you can see an example. Maybe because it is not as clear at the back of the room, but the presentation is online on the Turina website, the TNC conference website. So you are invited to take a closer look. So what this picture shows is an attempt to establish a 1 GeG path from allocation and end host in Chestnut in Brno all the way to a host in the Louisiana State University in the United States. And you can see with the different clouds which are the domains that were involved in this end-to-end path setup. You can see on the bottom, on the top right-hand side, the Jean2 cloud. You can also see the Hopi cloud. You can also see the LSU part. The light blue parts are Chestnut, and so on and so forth. And you can also see, if you can take a closer look, that each one of these networks use a different data plane technology to provide the service. So in order for these kind of circuits to be set up, the NOCs and the people involved had to call each other, exchange a large number of emails, and discuss the details of how to implement this. So what we are trying to do is to somehow streamline and automate this process. And I would like to repeat that this does not concern a dedicated facility. It concerns the publicly available infrastructure and resources of the research networks. So other issues which are involved in this process is authentication, authorization issues. How can you authorize requests when they arrive? And how do you make sure that an end-to-end provisioning instance is authorized and agreed among the domains, and so on and so forth. So the approach that we tried to follow was to have, and here is an abstracted example of what we are trying to do, is to define the processes and a system in such a way that control and provisioning happens in a distributed manner, in a way in which each domain involved can have its own role. We need, in the end-to-end provisioning process, to have business layer functionality like AI, policies, to enable advanced reservations. And also, we have to make sure that the privacy and the details of each domain, internal resources and availability and specific configuration details are safeguarded, and also that control of the resources within each domain remains within the domain. So this is a very quick overview of the approach that we took for designing this system. Like I said, you can find more details on that in the presentation later this afternoon. Very briefly, we devised an architecture where we have distributed control of resources. This is achieved where, in a way in which each domain has a different module for controlling its inter-domain communications, which we call the inter-domain manager, and another module that controls the internals of the domain. And in this way, we were able to separate the information that the domain communicates to the rest of the world and the detailed signaling and provisioning and monitoring that happens between its boundaries. We have broken down each of the two modules into different sub-modules. And the focus of my speech today is the purple box that you see at the bottom of the Autobahn system, which is called the technology proxy. So what I will try to describe today is how we have followed this architecture and these principles, and how have we already tried with developing the technology proxies that will allow the Autobahn system to communicate and operate on top of a specific domain, a specific NRN network. So in this architecture, the technology proxy serves as the intermediary between the Autobahn system that does the inter-domain work and the underlying network. For bandwidth on-demand services or light path provisioning or circuit provisioning, there are a number of different approaches from specific research networks. Roland earlier spoke about the SurfNet Direct solution. There are some other CLI-based tools like a BlueNet tool of HANet, the ANS tool of GearNet, and the Pioneer tool for configuring layer 2 MPLS virtual lease lines. Also, we have cases like that of the GÉANT network where a specific interface to the NMS allows for the provisioning of and a signaling of circuits or light paths between the edges of the network. So we can see that there are a number of per domain efforts to offer bandwidth on demand or dynamic circuit services. So what Autobahn, these are mostly intra-domain solutions, and what Autobahn tries to do is to be the glue that brings all these per domain, intra-domain, local provisioning systems to interwork with each other. So the requirements from the Autobahn architecture is for each network to deploy the Autobahn system as a controller for inter-domain operations, and then to contribute with the development of a technology proxy between the Autobahn domain manager module and the local provisioning system or the local data plane. Going back to the big picture, with a bit more detail this time, we can see now that the technology proxy has a publicly defined web service-based interface towards the Autobahn system, and we can also see that we have broken down the technology proxy into sub-modules so that each network can apply the solution which is more applicable to its current way of provisioning circuits. We have called these sub-modules vendor proxies. For example, the left-hand side vendor proxy is a CLI-based tool which directly controls the network elements. There are other cases where the vendor proxy communicates through the control management plane or the provisioning system of the domain to do local signaling. So the interesting part here is to see how can an NRN develop, honor, first of all, the interface between the technology proxy and the Autobahn system, and we can see some examples of vendor proxies that were developed and are currently interworking with Autobahn. It is important to say at this point in time that there are some modules, there are some parts of the Autobahn system which in some cases can be undertaken by the control plane or the local provisioning system, and the design of the domain manager of the Autobahn system is modular in such a way that this functionality can be split between the Autobahn system and the network. So just to give an example, if a domain, a network, wants to have full control of how requests are routed within its backbone, then the network can take this responsibility, and we can remove this responsibility from the Autobahn system and undertake this responsibility of pathfinding and routing the requests by itself through the corresponding technology proxy. So what does the interface between this technology proxy and the Autobahn system has to offer? It has to deliver and allow the exchange of topology and resource availability between the Autobahn system and the network. It has to enable communication and signaling requests, again, from the Autobahn system to the data plane. And also it has to be used for communicating notifications and errors from the data plane back to the Autobahn system so that this can be fed to the inter-domain neighbors and notify the end user when a problem arises. As already mentioned, due to the modular design of the Autobahn Domain Manager, parts of the functionality in the Autobahn Domain Manager can be substituted by management and control plane functions, like the Pathfinder or even the topology abstraction. A domain can choose to abstract its internal topology and export it to the DM through the technology proxy interface in a way that each domain sees fit. Here is an overview of the technology proxy methods. There is an ad reservation method which uses a reservation ID to uniquely identify its reservation and report status or update status between the network and the Audubon system. There is also a remove reservation function and a number of other methods related to failures and exceptions. It's a very simple interface, and it gives the freedom to the network and the system used within the network to provision circuits to map these functions into internal functions in a way which gives a large degree of freedom. Here is a small extract of what that interface looks like. As you can see, there are parameters, reservation parameters we call them. The Audubon system can signal to the domain requirements for a specific circuit regarding the maximum delay between the two edges of the domain, or whether that provisioning should be bidirectional or not. Also the start and end time. So it's a very simple interface. The requests come in and the responses are also received through that interface. We are currently working on it. We are experimenting with it in specific networks, and it is subject to further development and enhancements. What we have also developed is an installation guide for the system. So this guide provides details on what the Audubon system server specification should be, how does the software on the server needs to be configured, what are the port configurations that need to be made. There is also instructions on how to set up the communication channel between the neighboring Audubon systems in adjacent domains, how to install the Audubon system, and last but not least, we provide the documentation of the technology proxy interface and guidelines on how to implement the functionality below that interface which is required. Here are some examples of cases where we have developed this interworking. The first one comes by integrating the Alcatel ISN interface of the Alcatel NMS system used to control the Giant backbone. Actually, we have mostly worked with Giant testbed infrastructure, which is an equivalent to the Giant production network, but is just used for experimental purposes. So essentially, in this case, we had the domain manager of Audubon sitting on top of a technology proxy web service interface that was developed, and it was structured in the way that you can see in the right-hand side figure. So there was an ISN proxy developed between the Alcatel NMS and the Audubon DM, which was translating the requests back and forth between the two systems. So essentially, technology proxy interface requests were converted to ISN commands and vice versa. There is a number of nice findings through that process. There was a number of problems that we have to solve, as usually the functionality of the NMS and the functionality, the functions that the technology proxy interface of Audubon needs are do not have a one-to-one mapping. So we had to implement exception handling, rollback functions. There was some extra care for supporting concurrent requests because the requests from the Audubon side are synchronous and some of the ISN responses are asynchronous. And there are some more open issues like supporting signaling through the ISN interface on 10 gig interfaces, but we're working on these. Another example was trying to integrate Autobahn with the GRNet ANS tool. The ANS tool is a web service-based application which is used to provision GRNet QS and VPN services. It's a CLI-based tool, and for the case of the Greek Research Network, it acts as the Autobahn technology proxy. So again, here we had to adjust the workflow slightly to conform to the Autobahn model, which is a check for resources and then reserve. So again, we have the ANS tool mapping each call from the Autobahn DM to its internal functions and vice versa. In the case of the ANS tool, we were using this technology proxy to generate signal from the Autobahn tool and generate configuration for the GRNet backbone routers. Another example is the integration of Autobahn with the BlueNet tool. The BlueNet tool is the Irish Research Network's tool for provisioning port and VLAN mode links using layer 2 MPLS VLLs or over native clouds. And again here, HNet internally developed the workflow and the GUI for the BlueNet tool. The BlueNet tool has a front end for user requests and includes monitoring tools, and it automates the provisioning of end-to-end circuits. So in the case of integration with Autobahn, which is currently out of development, we had to map the Autobahn technology proxy interface methods to the BlueNet functions. In the case of HNet specifically, because of the principles in which the HNet BlueNet tool operates, there was a mapping, an abstraction of the HNet topology exported to the Autobahn tool through the technology proxy interface. There was also one last but not least effort of integrating a tool that Pioneer has developed with Autobahn, the Polish Research Network. So there was, again, a scripting tool developed for Pioneer to participate in the Autobahn efforts. The Pioneer data plane consists of Foundry XMR switches, and again here the configuration is done through CLI. So we had to develop the technology proxy between this tool and Autobahn. The tool is, in this case, we had to put some of the state of the circuit reservations within the Polish, the Pioneer tool, and some of it within the Autobahn DM. So there is a sharing of the responsibilities between the two. The Autobahn DM executes the path computations. The tool accepts a feasible path and implements it on the data plane. So these are a number of examples that show how can the Autobahn system be integrated with existing provisioning tool of NRNs. And these examples and these trials have given us a lot of useful feedback, have taught us many useful issues. And at this moment, we are trying to experiment with more networks, and we're trying to stabilize the technology proxy interface definition of the Autobahn system and do the same work with other NRNs who want to join this cloud. So currently, the Autobahn system is installed and under integration with the local provisioning systems in the NRN, in 6 NRNs. HNet, Pioneer, Chestnet, CarNet, GAR, and GRNet. And there are discussions and some initial thoughts to see how can we peer the Autobahn system with FCCN, Renater, Surfnet, and Nordunet. Since the 2 previous presentations were Surfnet related, I want to mention here that the thoughts for integrating the Autobahn system with Surfnet is to place the Autobahn system as the interdomain interface of the direct tool to the rest of the Jant facilities. So this means that we are following the same principle like we have followed with the NRNs that were presented here today. Another interesting issue that I would like to mention is that we are actually using all these efforts to demonstrate the establishment of end-to-end circuits from the 6 NRNs that I mentioned, who are already running it as a pilot, with endpoints across Internet 2 to a number of regional networks in the US and a handful of endpoints in ESNet. So essentially, each of the NRNs in Europe that have enabled Autobahn can speak through the GÉANT backbone Autobahn instance to the equivalent dynamic circuit network instances in the Internet 2, and this makes it possible to have signaling of circuits from hosts within the public NRN infrastructure in Europe to end hosts at the other end of the Atlantic. A demonstration of this capability will be made right after the session in the back room. So we will be showing circuits dynamically signaled between end hosts in this set of NRNs and GÉANT in Europe, and also between hosts in Europe and the United States. So I would invite everyone interested in this to visit us in the back room. It will take us, the demonstration is scheduled for during lunchtime. I would suggest that you show up at around 1 p.m. because this will give us also some time to grab some lunch. So this is my presentation.
Thank you very much. Are there any questions?
Aphrodite, just a short question. You mentioned the ISN Alcatel system. Is this related to the Alcatel GMPLS implementation, or is it just a management system?
It's a management. It's an interface to the management system.
Other questions? Vasilis.
Yes, the question has to do with the end user, the campus. How do you make sure that the campus network that goes to the end host gets dedicated bandwidth dynamically?
Okay, this question is probably of a more general scope. The issue we have tried to first of all solve the problem. Not exactly end-to-end, but edge-to-edge. So we have been working from an NRN edge to another NRN or RON in the United States edge. There are many reasons why we limited ourselves to this. One has to do with the fact that, for example, the NRNs don't have control over the campuses. But the architecture and the way the system is designed and engineered allows for campuses as well to install a local instance of Autobahn and to integrate it with their local provisioning tools so that the circuit can come from the NRN POP. It can go through the campus network and reach the end host. Whether the campus networks will adopt such a solution or not is entirely up to them.
Any more questions? If not, let's thank our 3 speakers and enjoy lunch.